A really interesting thing that we can do in a prompt is we can actually teach the large language model to follow a pattern using something called few-shot examples or few-shot prompting. So the idea behind this is we're going to give the large language model examples of input that we would give it and then the output that we would expect. And so you can imagine a human will go through a couple of examples. So they'll give it some input, they'll show it what the correct output should look like. They'll then give it another input, give it the correct output. And the idea behind this is that we're developing a pattern that the large language model can then learn to follow. So actually within our prompt, we're teaching the large language model a new trick. We're basically showing it what we want it to do and how we want it to format the output within a series of examples. So rather than describing the process we want it to follow, we're giving it examples of what we want it to do and then hoping that it will continue the pattern that we provide. So let's take a look at this. So if you'll see right here, we've got a simple example of few-shot prompting. So the idea behind this is we start off with input, and you'll notice that this is a common thing that you will see in few-shot prompting is that you'll see a prefix applied to the lines. Now you can have all kinds of prefixes, and your prompts and your patterns don't have to just be input and an output. It could be a couple of different steps, and we'll look at that in a minute. But as we see here, we have an input, which is the movie was a bit long. And what we're going to do is we're going to do what's called sentiment analysis. This just basically is try to analyze some comment about a thing and try to figure out what the user's sentiment was about it. Like, were they positive about it? Did they think it was a good thing? Or were they negative about it? Did they think it was a bad thing? Or were they neutral? And we're just going to do a really simple example with sentiment analysis where we're going to take some fake reviews of different things, and then we're going to decide if they were positive, negative, or neutral. So what we're doing, rather than saying, go and analyze these user comments and tell me if they are positive, neutral, or negative, instead what we're going to do is give a series of examples. So we give the first example, which was the movie was was good, but a bit long, and we say the sentiment was neutral. So it has some pluses and minuses. It was good, but it was too long. Then we have an example where we say, input, I didn't really like this book. It lacked important details and didn't end up making sense. And then we say the sentiment was negative. And then we have another input where we say, I love this book. It was really helpful in learning how to improve my gut health. And the sentiment is positive. And then what we do is we're going to give it the thing that we actually want to perform the task on, that we're going to hopefully get it to follow the pattern on. And we'll say input, I wasn't sure what to think of this new restaurant. The service was slow, but the dishes were pretty good. And then we cue it in to follow the pattern by saying sentiment, basically, tell us what you think about this thing. Now, my prefixes are a little bit leading. They are giving it information about what to do, but it could also learn from these patterns. If we just said input and output, it can also do that. I'm giving it a little bit of richer information. Now, my goal then is to get the large language model to go and analyze the input I give it and decide what should be attached to sentiment, and it picks up on our pattern and it says neutral. So it sees that in this review, it says service was slow, but dishes were pretty good. And so it's seeing that sort of positive and negative, and it's following my pattern that I gave it. I didn't tell it this is what neutral meant, but in the examples that I had before, a kind of a balance of positive and negative ended up being neutral. Now, a couple things to note. One, we didn't tell it what to do. Two, we didn't tell it exactly what the output should look like. And what we see is that it's constrained itself to the output and then basically the labels that we gave it earlier. We had negative, positive, and neutral, and it's automatically constrained itself and provided an output based on that. Now, it won't always constrain itself, but this is a nice thing. In many cases, this can help us get a more constrained or bounded output out of it. Now, if we went and we gave it a new one, we can say input, I really hated this coffee. It was roasted too much and tasted burned. Now, notice I'm not going to give it the prefix for sentiment. So let's see what happens when I do that. And then you notice it provides the prefix and the output that I expected. Now, The really important thing to think about with this is if you go back to when we talked about large language models and what they're doing, they learn to predict next word. They're learning patterns. And so when it sees input in a statement, it's predicting that the next word should be sentiment because that's what it saw in the examples that we provided it. Before, when we ended with sentiment, then what it did is it knew that it needed to pick up right after sentiment. So if we go back to this and we edit it, and we just add a line here and we say sentiment, then it should pick up the pattern right after sentiment. And so this is kind of helpful to know about when you're thinking about few-shot examples. Now this is a simple example of following a pattern, but you can see how this is a powerful way of teaching, particularly if you have data that describes the task that you want to do. And then when I say describes, it shows the input and it shows the output. And it doesn't necessarily describe how the task was performed, but we can see what's being done. And that type of thing can be a good fit for a few-shot prompt. Large language models can actually do some planning, which is an interesting ability. So they can actually go through and take patterns and with few-shot examples, and they can learn what the next action should be given a particular situation. But I'm giving you this example not because they're limited to, coming up with planning in the sense of actions or, doing sentiment analysis, but I want you to expand your sort of mind on what's possible with few-shot prompting and see it as a technique that can be taken and adapted to all kinds of situations. So we've seen how we can use few-shot prompting for doing sentiment analysis. Now we're going to do something very different with it. So we're going to take a look at this example where we're describing different situations with driving a car. So in the first one we say, situation, I'm traveling 60 miles per hour and I see the brake lights on the car in front of me come on. And the action is we're going to brake. So again, we've got a first example in our few-shot examples. Situation, I've just entered the highway from an on-ramp and I'm traveling 30 miles per hour. Action, accelerate. So we're teaching the large language model that it's going to be given a situation and it needs to decide what the car should do. Situation, a deer has darted out in front of my car while I'm traveling 15 miles per hour and the road has a large shoulder. Action, brake and swerve into the shoulder. Situation, I'm backing out of a parking spot and I see the reverse lights illuminate on the car behind me. And then we prompt it with action. We leave off at the end of our prompt with something that indicates to the large language model we want it to decide what the action is. And what do we see it do? It actually says stop and wait for the car to back out before proceeding. And it's making a sensible decision about what the action should be. Now, I don't think we should go and build self-driving cars with few-shot prompting. I don't think we're going to get there with that. But I do want to show you that we don't have to think just within a narrow, rigid box of classify something. We can actually kind of have complex tasks that we're having it perform. Now, sentiment analysis is a complex task, but this is also a very complex task that's sort of in a different vein. So I want us to think very creatively about how we can use few-shot prompts. Now, again, one of the things that we're getting is we're getting some constraints on our output. It's learning what the output should look like. Now, I'm going to then go and do something else interesting. I'm going to show you kind of an interesting capability of large language models. And one of the things that can be done to use one large language model to teach another one, which is kind of an interesting capability. So I'm going to say, please provide more examples, and then I'm going to kind of prompt it with situation. And it's going to start generating additional situations and actions. So it's learned from our pattern, the types of things that we're describing and the types of actions, and now it's going to go and generate more examples. So it says you're driving in heavy rain and notice that the road ahead is flooded. So this is the continuation of our situation. And then it says action, slow down and cautiously drive through the flooded area, watching out for other vehicles and avoiding sudden movements or changes in directions. I would actually disagree with this. I'm not sure that it's smart to drive through a flooded area. That's probably questionable decision making, which again just reminds you that you need to own the output of the large language model and check it. Situation. You were driving on a 2-lane road and a car is approaching you from the opposite direction with their high beams on. Action, dim your headlights to low beams to avoid blinding the oncoming driver. But you notice the interesting thing about this is it's giving us some rich situations and possibly appropriate actions. I'm not sure I agree with the flooded one, but we're generating different examples of situations and what to do, and they look very similar to what we produced before. And one thing that's interesting is we can actually take examples like this and then curate them and have a human edit them and then provide them back to a large language model either later as additional examples for our few shot examples. And so once we've had a human look at them and curate them a little bit, maybe clean them up, maybe we don't want that one on flooding because we don't think that's a good idea, so we actually say, well, you shouldn't drive across flooding, or we sort of spell out the rules. But you can imagine that the level of effort to create the initial examples right here is much higher than the effort to go through and generate subsequent examples, which we can then go and hand edit and curate. So we can quickly build up these examples, both in order to generate an output right now that we want, but also to generate examples that we can later give back to the same large language model, or that we could go and give to another large language model to teach it. And in fact, some people have actually gone and done this. They've taken output from ChatGPT, for example, and they've taken it into another large language model like Facebook's Llama and used the output from ChatGPT to improve the outputs of Llama. And so this is another interesting capability, is that large language models, through these few shot examples, they can generate few shot examples for other models. The other thing I just want to go back to is this is a very different sort of task and style than we had before. We have a situation and then we have an action that's being predicted. And so we can have all kinds of interesting things. Anywhere where we can have a pattern that we can describe, a set of examples that show the input and what we want the outcome to be. And we can also show things that have intermediate steps, which we'll look at in another video. The examples that we give in few shot prompts don't have to just be an input and an output. We can actually show intermediate steps to reach a particular goal. Now, one of the reasons why this is really interesting is that when we begin showing the intermediate steps, the large language model can learn how to apply a series of intermediate steps in order to reach the goal. So we can start getting more interesting output than just here's an input and here's the output, or here's a situation and here's the action. We can start looking at, if this situation occurs, what might be the next action, and then the action after that, and the action after that, until we reach some state that is important to us, like we are, no longer at risk of running into the car in front of us. And so if we tailor our examples correctly, we can actually have the large language model do sort of the intermediate breakdown of the problem into a series of steps, or we can have it decide how it might go and tackle the problem. Now, let's look at an example of this. We're going to take our car example from before, and now we're going to enrich it a bit. So we've now got actually two essentially situational examples. We start off with one, and it's the same one from before. The situation is I'm traveling 60 miles per hour, and I see the brake lights on the car in front of me come on. And then we say, think. I need to slow the car down before I hit the car in front of me. Action. Press foot on brake. Think. The car isn't going to stop in time. Action. Check if the shoulder is wide enough to swerve into. Think. The shoulder is wide enough. Action. Swerve into the shoulder. So now we've built a more complex scenario that includes the original situation, but then we have sort of updated steps of what's happening and what the thought process is and what we need to do next based on that thought process. So in this case, we're traveling down the road. Suddenly the brake lights on the car in front of us come on. We think that we're going to hit the car, so we hit the brakes. We think that we're not going to stop in time, so we look over. We see that the shoulder is big enough, so we decide to swerve into the shoulder. And so we're now basically having a more complex situation that also has multiple steps involved. Similarly, we've taken one of our other ones. that we had before. I've just entered the highway from an on-ramp and I'm traveling at 30 miles per hour. Think, I need to speed up to the speed limit so that I don't get hit from behind. Action, press foot on accelerator. Think, I've reached the speed limit. Action, let up on the accelerator. So we're basically going through, we're breaking down the problem or situation into multiple steps and what's happening. Now we provide a situation, again, the parking lot situation. I'm backing out of a parking spot and I see the reverse lights illuminate on the car behind me. Action. And so now we're prompting for what we would like the large language model to decide. And now we see, instead of just a quick, it's done, look, stop, wait for the car behind me. Instead it says action, immediately stop backing up. So we see immediately stop backing up, and then it thinks, I need to check my surroundings to make sure it's safe to continue backing up. And then action, check mirrors and surroundings for any obstacles or pedestrians. So it's thinking about what does it need to do next. It's thinking, oh, I need to look around and make sure it's okay. So it looks in the mirror, and it looks in the side mirror, the rear view mirror, the side mirror, and then it thinks, okay, it's safe to continue backing up, and so action, continue backing up slowly and carefully while keeping an eye on surroundings. So now we've got more sort of fine-grained detail in what we're actually going to do in the particular situation. Now, there's all kinds of interesting things where we can imagine doing this. We can think about customer service. The customer is reporting a particular problem, and we've recorded what customer service agents did to help the customer solve that problem. And so we could imagine that through few-shot examples, the model could learn to help a customer diagnose a problem. And if it had seen enough different examples and enough different paths, it could go through and figure out what to do. We can also, like last time, we can generate more examples. So we can say generate another example, and it says generate, situation. I'm driving on a narrow, winding road with several blind curves. Think, I need to slow down and be cautious to avoid any potential collisions. And it goes through a series of actions until it says resume normal speed. And then we could say, think, I am running out of gas. And it says, think, I need to find a gas station before I run out of gas. Action, check the GPS or map for nearby gas stations. Think, the nearest gas station is too far away. Action, reduce speed to conserve fuel and try to make it to the next gas station or rest area. But you can see how we're getting a script. It's sort of like a problem-solving script. Now, let's think about this if we're the customer service. We might want to go and generate a sequence of actions, and then we could input what the next response is that we get from the customer. So let's look at where we end off on this example. Action, pull over to the side of the road and turn on hazard lights to signal other drivers. Call for roadside assistance or walk to the nearest gas station as possible. Think, roadside assistance is unavailable and the nearest gas station is too far away to walk to. So let's see what it decides to do. Think, I need to conserve my phone battery and find a way to get to a gas station as soon as possible. Action, check if there are any houses or businesses nearby where I can ask for help or use a phone. Think, there is a house in the distance. And so you can see how it's building up the script of what to do. It's doing problem solving, it's creating interesting situations. We can also prompt it to keep going. We can keep having it go further based on inputs, like what would happen in this situation? How would you go about dealing with it? We also see that the input is fairly constrained in what it's giving us. It's still following our pattern. Now this is a key thing to go back and think about is the intuition behind this. This works partly because this tool knows how to predict what's next given a pattern. It's learning from language, given this pattern, this is what I do next. You can also imagine that it's seen in its training data lots of scripts, things that looked like, okay, here's what is going on. You can almost think of like a movie script. So-and-so said this in response, and then you might see a description of what was happening. Well, they get into the car, exit scene, something like that. But, we're using patterns, we're using structures that are likely to have been things that it was trained on and seen. So it's learned how to, from these examples, go and extrapolate what should happen next. The patterns and its ability to learn and intuit what needs to come next in the pattern is based on that it's seen these types of things. Now, if we went and we picked some type of pattern or structure that is very different from what it's seen, it may be able to do it, it may not be. So one thing to think about is when we're structuring things, try to pick simple patterns in terms of how we structure the text. They're going to be something that it's likely seen, something similar to in the training data. So this idea of a prefix with then some situation, an action, think about trying to pick a format like that looks like something it's seen. Notice another thing, we're keeping each example, although it's wrapping around here, these things are actually each one line. So it gets much harder to follow the pattern if we say like action colon, and then we have a whole bunch of stuff on multiple lines. It becomes harder to see the pattern because not every line starts with one of these prefixes. So you have to think through the structuring and the formatting of these things, but at the base of it all, we're trying to give it some pattern that it can quickly and easily pick up on in order to understand how to solve the problem. We can provide the intermediate steps like we're seeing here, but we don't necessarily have to give it the logic for how to decide the next step. In fact, if we think about this, when we say roadside assistance is unavailable and the nearest gas station is too far away to walk to, if I had to describe the rules of how to do that and this whole situation that we're going through, if I had to really write a prompt that had all the different rules, in this situation do this, in this situation do that, you can imagine it would take up a lot of space and it might be really hard to do. Probably is going to have limited flexibility. So one of the powerful things about these few-shot examples is we can tap into the large language model's reasoning, or whatever we want to call it, its computational abilities, to go and figure out what's next and come up with the next item in the pattern. Let's look at some examples of where we're making mistakes in our few-shot examples, of things that we can do wrong in the formatting of our prompts, and what we can kind of think about and learn from these examples. So here's some few-shot examples, and the idea behind this is we put together a not very good prompt to analyze how hard things are. Like, is it soft or hard? That's what we're trying to get at with this prompt and some few-shot examples. Now, this is not a good prompt. This is a bad prompt, and we'll see why. So what we've got is we have input as the prefix. We've then got brick. We've got output as a prefix, and then hard. We've got input as a prefix, and then pillow, output soft, and then we've got input car. Now, notice what we've got here. One, we don't have a lot of examples here, but two, we've kind of switched gears. Like, we started talking about input and output and the hardness of things, using things that are really obvious, probably. Like a brick is hard, a pillow is soft. Is a car, I guess a car is hard, but it's not as clear what we're getting at. We also might just be trying to describe some fundamental sort of intrinsic capability or properties of this thing. It may not be about hard or soft, because it could be other things. It could just be an attribute to describe the thing itself, because pillows are generally thought of as soft and bricks are normally thought of as hard. Those are kind of fundamental descriptors sometimes that you use for them. And what we see is that when we prompt ChatGPT in this example, what we get is it says fast or maybe transportation. And so this kind of shows us a couple things. This is a prompt that's not very well designed. And because of that, what we see is that ChatGPT isn't quite sure what the next output should be from the pattern. Now there's a couple mistakes in here. One is we've got input and output. Input and output are really generic prefixes. They don't really give the language model much information about what the task is that it's trying to do. All we know is we're taking in something and we're getting out something, but it's not really telling us, what it is that we're describing. Like maybe we should go and say, input, brick, surface feeling, hard, input, pillow, surface feeling, soft, or maybe it's something about like if you hit it, what will it feel like? There's all kinds of things we could do to give it more sort of context around what we're trying to get at. We could also give it more examples. But what we've got here overall in this prompt is we've got a lack of information. It's not detailed enough, and we're not giving enough information about what the task is that's being solved, and the result of that is that the language model isn't really sure what the solution is. Now, one way we could solve this is we can go and before we give our examples, we could give a little bit more context, so we can provide some instructions. So we could say your output can only be soft or hard. Now, one thing to notice is I'm putting these things in quotation marks to try to indicate to the language model that these are the two values. I don't want it to get confused and think I'm talking about soft or hard in some other context, but I'm putting these things in quotation marks, trying to giving them some emphasis that either it's soft or hard. And this may not always work because we still have a prompt that's really generic, that really doesn't have a lot of context and a lot of meat to it. It's still very vague. We've got input, brick, we're still dealing with it. Now, luckily in this case, adding this little bit of additional context and specifying to the large language model that we only want soft or hard as an output helps it figure out that it should think about if I pushed on this car, how would it feel like? It would feel hard, and that's kind of the task that's being solved, and so it comes back with the right thing. But that's a first thing to think about. When you're writing few-shot examples, are your examples detailed enough? Are your prefixes that you're using for these things meaningful? Do they give additional context that the large language model can use to figure out what the next thing in the sequence is? Another way to think about it is if you gave this to 10 different human beings, would you have a chance that a few of them might be confused about what you're trying to ask for? And if the answer is yes, then you probably need to think about how to refine your prompt. Like if it's not fully clear what you're trying to do in the examples or what the process behind the examples is illustrating, then you're probably not detailed enough. Now, one way you can solve that is by adding some more instruction like we have here at the top of this prompt. Now let's look at another example. I've got object plane, speed fast, object worm, speed slow, and then I go through a series of examples, and notice I'm giving a little bit more context here. My speed prefix is a little better, right? Because speed seems something that's quantifiable, right? Like a plane is fast, a worm is slow. Like that should be more context. And so we then go prompt it with object ball, speed, and this is another important thing to realize is it says variable. And so one of the things we have to think about is we're trying to get the large language model to produce an output or to classify or to fit into some boxes. We need to make sure that it gets enough information in the input to be able to accurately put things into the boxes. So we need to make sure that whatever information we're giving it about what it's going to do always has enough context that it can make a decision about the label. Now in this case, a ball could be fast, it could be slow. If I shoot a ball out of a cannon, it might be going really fast. If I shoot a ball, if I put it on the top of a rocket, it might be going really fast. There's all kinds of different things that could make a ball go faster or slower. So we have to make sure that we provide enough context. Now, in general, the thing to think about is, am I giving enough information? Now, I'm going to go back and I'm going to change my prompt now, and I'm going to say object, ball kicked by a baby, and then we get immediately it says slow. So when you're building up the few-shot examples, you want to make sure, one, your prefixes are pretty descriptive. Two, do the examples that you're giving really give enough information to derive what the underlying process is that is going on in order to go from the starting input to the final output? Do you really have enough information there to see what's underneath the hood? And one way to think about that is if you asked a bunch of humans, would they all know exactly what you wanted it to do without any ambiguity? Two, you want to make sure that you have enough description before the examples if needed to provide additional context. Sometimes examples, you're just not going to be able to get there with examples, and you may need to provide some additional rules or other information at the start of your prompt to help it along. And so really a lot of times what you're thinking about is you have a limited amount of space in your prompt, and you have to think about, is this something that I can better describe in an example, or is it something that I can better describe in some instructions at the top? And what better means is, will I get a more accurate output, and will it take less space or maybe less words to describe it? If I can get it done very clearly in an example, then maybe that's the right way to go, if that example doesn't take a lot of space. On the other hand, if it's a really simple rule and I can describe it, I may be able to get a better response, by putting that rule up into the description. And then finally, we have to make sure that we provide enough information. So in this example, ball kicked by baby, if we're trying to bucket things or we're trying to get a particular output, we may have to make sure that when we give input, that there's sufficient richness and detail in that input to follow the rules or prior examples that we've given. Now, this is particularly important if our prior examples were pretty clear cut. It's probably something better. Now, one could argue that our prior examples, if we go back and look at this, we said a plane was fast. Well, a plane might not be fast, right? A plane might be slow. It might be sitting parked on the tarmac of an airport. And so we also want to make sure that our examples are rich enough and detailed enough. Now, sometimes we can get away with simple things like plane, fast, worm, slow in order to teach it, but sometimes we're going to have to go into more detail. We're going to have to provide more context. So make sure and think about, do you have enough real information? Is it going to depend on the situation, those things like that? Provide details. Now, one way to do it would be to say, just make some assumptions, but one of the things that can happen sometimes when you do that is you may get more verbose output than you really want. It may not fit into that bucket. But when you're writing these prompts, think meaningfully about what is a meaningful prefix? What information or instructions do I need to have at the top? And can important information be better conveyed as an instruction at the top or as an example? Do my examples cover the space enough? Do I have enough good examples with rich detail for it to learn from and derive what the underlying process is? And then when I go and I give it the new input, do I make sure I have enough relevant context and information with the new input in order to apply the process that I taught it? Because we may teach it the process really well, but then give it a new input that just fundamentally is missing information in order to apply that process. You may remember being told to show your work when you were a student, probably in elementary school or middle school, and you were working on a math exam, and you had to explain how you got there. Or maybe if you've gone on and you've done other things where you had to prove, that something was true that you had decided. And so showing your work, explaining your reasoning is something that can be really important in a number of different domains. And it turns out that when it comes to writing prompts, this can be really, really important. Getting an LLM or a large language model to explain its reasoning behind something actually can make the large language model perform better for us. Now, this is a really interesting thing, but if you think about it, it kind of makes sense, right? Because we have a large language model that's trained on different patterns of text, and it's learned to predict what comes next. So if it can explain its reasoning correctly, then it's more likely that it's then going to produce the right answer, because the right answer sort of intuitively should come after the correct reasoning. Similarly, if you think about it, if it starts explaining the reasoning correctly, if it gets the first step right, it's probably going to get the second step right because it may have seen similar problems reasoned out. Now, this is an intuitive explanation. This may not be right, but I think intuitively you can kind of think about it is that if you break down the problem you're solving into multiple independent steps and you explain them and there's sort of a natural sequence and logic and flow to them, it's more likely that the final output, which is the answer, is going to be a natural extension of the correct reasoning and therefore correct. It's more likely to be correct if your goal is to accurately predict the next token. Similarly, if you have the problem and you get the first step right and the second step right, you're probably going to get the third and the fourth as a large language model because you've been trained on this stuff. So there is a technique for this, and it's called chain of thought prompting, and I'm going to show you examples of this. But it's really helpful to remember when you're building prompts that require some sophisticated sort of intelligence and reasoning capabilities. Now, we don't always need this type of breaking the process down step by step and explaining the process. But when we do, and we need that more effective reasoning, it's really useful to understand how chain of thought prompting works. So I'm going to start off with a positive example where we use it and we show what it does and how it works. So we have some examples here that we are going to give. Sorry, I'm actually going to start off with the negative example first. I apologize, that was a mistake. So I'm going to start off an example that does not use chain of thought prompting, and I'm also going to show an example where I'm going to make a mistake in how I phrase the prompt and how I structure the prompt. And I'll come back to this mistake in a second. But what I've got here is I have three different questions that require some reasoning. In the first two, I've given an example of what I want. I say, I have 4 bike racers start a race and travel an average of 30 miles per hour. They each race for 2 hours. Is the total number of miles ridden by all riders greater than 200? And then I have an example and I say answer yes. And then I say a question. I have a staging process for a bike race to line up racers. It takes 47 seconds to stage a group of 8 riders and 67 seconds to get the group to the starting gate and ready to race. I want a new group to start the race every 30 seconds. Do I need 8 groups staged at all times in order to have races continually starting every 30 seconds? And the answer is no. This is the example I'm giving it. And we'll see the reasoning behind these in a minute. And then I say, I'm in a spaceship without gravity. I have a cup with a needle in it. I move my foot on the bed, knocking over the cup onto the floor. I lift a book up and put it on a desk. Is there anything on the floor? Now, this is the question I'm trying to get ChatGPT to answer. And so I've given it basically some examples of questions with answers of either yes or no. So I'm trying to elicit a yes or no answer from ChatGPT. I'm using few shot examples to do that. And I'm showing it questions, I'm showing it answers. And then I'm asking it for the answer about this question about a cup knocked on the floor. Now, I have actually seen some variations of this, and I apologize because I don't remember exactly where I saw this first example of reasoning with the cup and the needle inside of it knocked on the floor. But I thought this was an interesting one because it works really well for showing the difference between chain of thought prompting and without. So this is without chain of thought prompting. So what does ChatGPT say? Because we asked it, is there anything on the floor? So the question was, I'm in a spaceship without gravity. I have a needle with a cup, or I have a cup with a needle in it. I move my foot on the bed, knocking over the cup onto the floor, and then I have some irrelevant information, and then I say, is anything on the floor? Now, without chain of thought prompting, it says yes. When the cup with the needle in it is knocked over onto the floor, both the cup and the needle will end up on the floor. In the absence of gravity, objects will not fall downward as they do on Earth, but they will still move in response to forces applied to them. In this case, the force applied by your foot knocking over the cup will cause the cup and the needle to move and come to rest on the floor. Lifting a book and putting it on a desk does not affect the position of the cup, so they will remain on the floor. So it says, yes, there's going to be something on the floor, the cup and the needle. Now, let's look at the same example, but with chain of thought prompting applied. So here we go with chain of thought prompting. So with this one, we've spelled out the reasoning behind each of the examples. So we go back to the bike racer. And we say, will the total be greater than 200? And so we say reasoning. Each rider will ride 30 miles per hour times 2 hours equals 60 miles. I have 4 riders. Therefore, the total number of miles ridden by the riders is 4 times 60 miles equals 240 miles. And then answer yes. This is chain of thought prompting. We're explaining the reasoning behind the examples to the large language model. So in this case, we're explaining, we're sort of working out the math, showing our notes of how we got to this answer. And then we do the same thing for the next one, where we're staging a bike race and we want to figure out how many people have to be staged at a time in order to start a race every 30 seconds. And we give the reasoning. Each group takes 47 seconds plus 67 seconds to be ready to race. So I will need to calculate how many races will need to be run before a group is ready to race. A group will have 114 seconds over 30 seconds equals 3.8 races run before it is ready to race. I can't have a partial group, so I need to round up to 4. I only need 4 groups staged to be able to race every 30 seconds, so I do not need 8 groups. Answer, no. And so you see, rather than just say, here's the example, here's the answer, we say, here's the answer, here's the reasoning, and then here's the answer, the correct answer. So then in this final example with the spaceship, again, we're having the spaceship, there's no gravity, we have a cup with a needle in it knocked on the floor, and then in this example, we tell it to provide its reasoning first, and then its answer. So we're prompting it and giving it a format that makes it clear we want the reasoning first and then the answer. And what's interesting is we see different reasoning than we saw before, and we get a different answer. If you remember before, we got the answer of yes, their cup and the needle will be on the floor. But if you look down here on this one at the bottom, we can see that it says answer no, because there's no concept of on the floor in a zero gravity environment. So if we look at this one's actually giving us sort of a better reasoned answer, in my opinion. Now there's probably different nuances, and I'm not an expert on this, but I think if you don't have gravity, you're not necessarily going to have the cup and the needle resting on the floor just because they got knocked off. And so the reasoning is better. In this one it says, in a spaceship without gravity, objects do not behave as they do on Earth with gravity. When the cup and the needle is knocked over, the cup and needle will not fall to the floor as they would on Earth. Instead, they will float in place or move in the direction of the force applied to them. And so, therefore, in the absence of gravity, there's no concept of objects being on the floor as we stand them on Earth. And so basically what it's saying is like, well, you might move them or cause a force to be applied, but they're not going to just sit there on the floor because there's no gravity. And so it comes up with the answer no. So you see right here, we're getting a completely different answer out of the large language model. And the difference is that one example, we're giving it the examples, we're giving it the reasoning behind the examples, and then we're asking it to provide the reasoning and then the answer, which is this case, and where we're saying no, there's nothing on the floor, which is probably a better answer in this case. In the other example, all we're doing is saying, here's the question, here's the answer. Here's a question, here's the answer, and we're not giving it the reasoning. And then finally we're saying, here's a question, and it's going to try to produce the answer first, which is what it does. And so the difference is really only in what it does. Here it's answering first, but it's not explaining its reasoning first. And its reasoning actually isn't quite as good, and its answer isn't quite as good. Now, spaceship, knocking a cup with a needle off on it, this might not apply to you, but it's an interesting example of where there's more nuanced reasoning. And if you have a case where you need to have it think through, and I say think very liberally here, but if you need it to try to get better reasoning behind the answer or a better computation, whatever you want to describe it as. But intuitively, if we've thought through the process of getting the answer, and we have a good process of breaking down the problem and going step by step to a solution, we're likely to get a better answer out, a better solution out. And so that's what chain of thought prompting is doing, is we're trying to elicit that break the problem down into steps. Think about, step by step how you're going to solve it. And the way that we get there, the way that we get to do that is when we give it few shot examples like we do up here, we explain the reasoning behind the answer, and we explain the reasoning first. We say, this is what I'm thinking and doing. This is why I'm getting there. Similarly, we do it on this one too. We say, here's my reasoning, and we provide the reasoning before the answer. And the goal is to get the large language model to do the same thing, to follow our pattern of breaking down and explaining the reasoning before giving the answer, to think through the problem, to give the fundamental steps, and then to produce the answer. And we get better outputs in this case, and in most cases it's been shown that you're going to get a better reasoning out of the large language model if you have it explain its chain of thought, what it's thinking through, what it's trying to do in order to solve the problem, then you'll get a better answer out. Large language models, as powerful as they are, they can't do everything on their own. they're going to have to reach out into other data sources, and they're going to have to learn how to use other tools to be really effective over time. So one of the things we have to learn how to do is build prompts that can allow the large language model to essentially reach in and query new information, to use other tools that can help it do reasoning or computations that it fundamentally is not designed to do. And so how do we go about doing that? So one way of doing that is with an approach called ReACT. So the idea behind this is that we want to teach essentially the large language model how to think through a process and understand steps where it needs to go and use some other tool, to take some other action outside of it and get the result of that tool and bring it back in as some type of computation or result that it can then incorporate. And so there's a specific way of writing prompts to do this. Now, this is similar to chain of thought prompting like we saw before. We're going to use some of those same concepts from chain of thought prompting, but we're going to expand the approach to have this concept of certain things that the large language model knows it needs to use some external tool to perform. So let's take a look at this. Now bear with me because this is a longer example. We're going to do a single example that we're going to teach the language model with, and then we're going to ask it to perform the same task. So in this example, we have a task which is calculate when I need to arrive at the Music City BMX national race for my son to be on time for his 9 to 10 open race. So BMX is a bicycle racing sport. Some of my examples lately have been around BMX. And Music City BMX is a local BMX track here in Nashville that hosts one of the big national races for BMX racing. And so one of the things is I need to figure out when do I need to show up at the track, because these are all-day, multi-day events. And sometimes you may want to figure out how late can I sleep before getting in the car and driving then in order to arrive. And what happens is in these races, you have hundreds of individual little races that are essentially like 30 seconds each. These are called motos that are run. And you want to figure out when you're moto 87, for example, well, how long do I need to wait after the start before that race is going to start? And so sometimes there's a balance there of trying to figure out when do I need to be at the track actually, as opposed to when does the race start. And so what we're going to do is we're going to have it solve this problem for us. We're going to pretend to solve this problem. This isn't actually solving it, but we're going to show you how this process works. So we give it a task and we give it an example, which is calculate when I need to arrive at the Music City BMX national race for my son to arrive on time for his 9 to 10 open race. And then we say think. I need to find out what time the first race begins. I can use a web search of the Music City BMX site to get that information. So remember, this is our example. So we're saying, here's the thought process. I need to first figure out the first step. Now you remember back to chain of thought where we're trying to have it explain its reasoning. Well, we're kind of doing the same thing. We're explaining the reasoning behind it. So we're saying, I need to find out what time the first race begins. We're explaining what we're trying to do. I can use a web search of the Music City BMX site to get that information. And then we have the next thing we do, which we say action, search, and then we give the Music City BMX website. And so action here in the search is basically a tool that it's learning to use. It's learning to use some external tool, in this case a web search. So it knows that there's certain information it does not have, and so we're teaching it, when you need information that you don't have, go and search for it, and you can search for it with a website. And then it says the result, we tell it, is all races start at 9 a.m. So then we say think. I need to find out how many motos run before the 9 to 10 open race. Motos are essentially the individual races that are going to run before that race. I can use a web search of the Music City BMX site to get that information. And then we show it again, another example of searching, assuming there's a search tool available to it, for the Music City BMX site. And then result, we show it the result. There are 30 motos that run before the 9 to 10 open race. And then we say think. I need to find out how long each moto took last year. I can use the video live stream from the USA BMX website and record how long the first 10 motos took. And then we say action video, and we give it some fake video and pretend that, hey, we were able to go and pull this video down and time something. And then result, the first 10 motos took 5 minutes. Think, if 10 motos took 5 minutes, 30 motos will take 15 minutes. The race starts at 9 a.m., so I need to arrive before 9:15 a.m. when the race starts. I will arrive 30 minutes early at 8:45 a.m. to be safe. So remember, this is our faux example. We've kind of imagined a scenario where I need to solve this problem, and I'm using a series of web searches and then watching a video from a prior year to figure out how long things took. And I'm trying to teach the large language model, in this case ChatGPT, to use these same tools to solve the problem. So then I ask it, here's the new task. Calculate what time my 36 to 40 novice race will end at the USA BMX Grand Nationals. And then I say think, to prompt it to start thinking what is the next step. And you'll notice what it does. It then says, I need to find out what time the first race begins at the USA BMX Grand Nationals. I can use a web search of the USA BMX site to get the information. Action, search, USA BMX Events Grand. So notice it's picked up on a couple of things. It's picked up on the idea that it has this tool called search that it can use to go and pull in information. You'll notice it's also picked up on the format of the URL. Now, this format I had was just completely fictitious in this example, but it's picked up that, oh, there must be this formatting, there must be a pattern behind these URLs that I can use, so I can go and search and use some knowledge of the structure of those URLs to pull in the right information. So it's learned, essentially, how to go into a web search. And then it says result. Note, as an AI language model, I'm unable to perform web searches. Please assume a hypothetical result of the purpose of this exercise. The first race begins at 8 a.m. Now, what's interesting here is if we were actually integrating this into a real system, we could have the system, whenever it sees a result, stop, pull in the actual result, put it in there, and then basically feed this first chunk back to the language model to then continue the process. So we don't actually have to worry about if it's going to fake the rest of this. We could just have it go, and we could incrementally get to each time we get a new result out that we actually need to fill in, we could go and run the web search and fill in that result. It then keeps going. It says, I need to find out how many motos run before the 36 to 40 novice race at BMX Grand Nationals. I can search, and it goes and searches on the grands, and then it has a hypothetical result. There are 120 motos. Goes and thinks again. I need to find out how long each moto took last year. I can use the video live stream, and then it picked up on the URL pattern. So you notice it's learning a lot of things. It's learning how to use the tool and how to input data in a particular format for it based on what I showed. It then says, okay, here's the result from that. And then it says think, if 10 motos took 6 minutes each, or took 6 minutes, then each moto took an average of 0.6 minutes. Therefore, 120 motos will take approximately 72 minutes. The first race starts at 8 a.m., so the 36 to 40 novice race will start around 9:12 a.m. I need to find out how long the 36 novice race itself will take. And it goes and does that, and then it says if the 36 to novice race starts around 9:12, then it will end around 9:15. This is the approximate time my race will end at the USA BMX Nationals. And so what's interesting is that it actually ended up in the end getting slightly off track. It gave me the begin and end, so it's telling me the begin time, but it also went and calculated the end time, which I may or may not want. But the more important thing is that along the way, it followed my pattern. Up here, I taught it this concept of searching. So I had action search, musiccitybmx.com. I had another action search for musiccitybmx.com. I had an action video right here, and it learned how to use these tools, and then it's applying the exact same tools down here. It's applying search, it applies it again, then it applies video, and it's applying it using the format. So you can imagine it's essentially learning to, run a web search, to watch a video, but again, these are tools, so it could basically go and send some information off to the tool, get an answer back, and then pick up in its reasoning. Now, the way that we would do this is we would have to have a way, if we're going to use this, to actually, when it gets to the point where it says, here's what I'm going to do, we would stop it and go give that data to the real tool, get the answer, and then come put it in for the result. And then we would feed this whole thing back in with the correct answer as the prompt. It then hopefully will run through up until it gets another action, in which case we would go and get the real result from that tool, put it into the prompt, and continue. And we would continue down until we got to a point where we had an output. Now, a better way of doing this would be to have some way of it saying, okay, I'm done, and I should have put that into the prompt here. But this is doing basically, it's teaching it, here are some tools that you can use if you use this format. So you can go and run this particular tool and you describe the tool to it. Now, other ways to do this, you can also, if I didn't have every tool used, I could have edited this prompt and I could have had a description of each tool and the format and other information that it could use to help it figure out which tool to use. Now, in my simple example, I did it just based on giving it patterns that I had directly in the sort of the few shot examples that I provided. But you can also have other ways of sort of catalogs of tools and their descriptions so it can think about which ones to use at the appropriate time. And you see how it's beginning to reason and know, which tool do I need to use at which point in time to get which type of information. So you can teach it to do this sort of problem solving so you can go and integrate it with other tools, and you can build these prompts that allow it to tap into other tools. And you see this in a variety of different frameworks. There's a tool you may have heard about called LangChain, which is a framework for writing these types of automation processes. And they use React underneath the hood in order to be able to go and do some of the interesting things like this that they do. We're going to be faced with the problem with prompts of the large language models themselves are going to be moving very rapidly. They're going to be continuously evolving, and we've already seen that. We've seen ChatGPT and GPT-4. We've seen Llama and Alpaca. We've seen Vicuna, and lots of different ones are continually coming out. And one of the things we want to know is when we develop our catalog of prompts, our patterns, we put lots of work in developing prompts that work well for us. How do we evaluate them and make sure that they're maintained over time? Because if we change our large language model, does that mean that all of our prompts are going to break? Or if we change the data that we're working on slightly, does that have ramifications for us? So we need better ways of helping to evaluate the output. Now, one way, of course, that we're going to do this is we're going to have humans look at the output in many cases. But we'd like to do things that could probably help us scale better, be able to actually go and do sort of large-scale automated analysis in some way. So how do we go about doing this? Well, one of the really interesting things with large language models is we can actually use them to evaluate themselves. This can be one of the inputs that we use to help determine how good our prompts are and how maintainable they are over time, is we can use a large language model to grade either itself or the outputs of another large language model. So we've seen the examples of this where they've actually taken large language models and they've had one large language model teach another large language model essentially. But we can do something similar in that we can take outputs from a large language model and actually feed them back into the model itself to grade them, or we can actually go and take another large language model that we're working with and have its outputs graded by, for example, a better large language model, maybe with more parameters that has more powerful. So let's look at an example of this and how we might build a prompt to do it. So in this example, I'm going to teach the large language model, in this case ChatGPT, how to grade the output of a prompt. I'm not actually going to show it the prompt in my example. I'm just going to teach it the grading process so that it can help automate it for me. And so I'm going to use some few shot examples. So as input here at the top, I'm saying here's my input, and it's a bit of text about Vanderbilt University from Wikipedia. It identifies that Vanderbilt University was founded in 1873. And I explain, here's what the output was. The output was, the following is a list of events and dates in the output. Vanderbilt founded in 1873. And then the explanation is that the output has unwanted text at the start and should only include the names and dates. And so I gave it a grade of 5 out of 10. So this is the output that was produced, and then I'm providing a human explanation of what is wrong with the output, of why it's not getting a perfect score. And then I'm grading it and giving it a 5 out of 10. So I'm going through and I'm doing a couple of these by hand to show it what I want. And then I'm giving it another example with that exact same piece of text I'm saying the output was just 1873. And the point of this is that, if you can probably sense it by now, is I want a prompt that's going to extract events and the dates that the events took place. And that's it. I want an event name separated by a comma and then the date of that event. I don't want any other text. I don't want explanation. I just want names of events and dates. And I'm showing how ChatGPT can grade the output to see if it's matching that format. I'm not even showing it what the prompt is. I'm not showing it what the task is. I'm giving it examples to help learn. And then I say explanation. The output is missing important information about the event that happened on that given date, and I give it a grade of 3 out of 10. And then I have one more with the input, which is that same paragraph about Vanderbilt. I show Vanderbilt University, 1873, which is the ideal output for my fictitious task. And I explain that the output exactly, and then I actually cut it off. There's a typo here. It's really supposed to be met expectations or something like that. And then I give it a grade of 10 out of 10. What's interesting is this doesn't even matter that I made a mistake here in my explanation because it still works. And so then I give it a completely different input. I say, here's a different input. Again, it's about Vanderbilt and the history of the English program at Vanderbilt in creative writing. And so I give it as input another piece of text on that. I say the output was, and I give it what the output was, the fugitives and South agrarians, first half of 20th century. And then Vanderbilt is a founding member of the Southeastern Conference, 1966. And that's essentially a prompt for ChatGPT to then go and grade that output. And so it then provides an explanation of the output. It actually mentions something that I didn't grade in there, but it's interesting. It says there's inconsistent capitalization. And then it gives it a grade of 9 out of 10. So as a human labeler and a human performing this task, I actually ended up with a 9 out of 10 because I wasn't consistent in capitalization. But you can see it did a good job. It took the sort of substance of what I wanted and it performed the grading task that I had given it. And so we can actually use large language models to evaluate the output of prompts. Now there's a number of ways you could potentially use this. One is if you have some system that's going to go and make decisions or generate information with a large language model like ChatGPT or some other model that you're running, you might want to have the model check itself or another model check itself, or you might want to do this multiple times, where you take the output that you're getting and you give it a grading criteria similar to what I've done here, and you've developed a prompt with grading criteria. You might have multiple prompts with grading criteria, and you all have them score the output. And then if the score is below some threshold, well, maybe you want to have a human look at that output, or maybe you just want to retry it and see if you can get something better to be produced. And so this gives you an extra sort of tool of how do we go and evaluate what's coming out, make sure it looks good, and still have sort of the power and sophistication of these models. And this is one way to do it. Now there's lots of ways that you could phrase the prompt. You might want to go and look at the alternative approaches pattern to develop some different ways. This is one example using few shot examples. Now I could have gone back and say, we could have said act and use the persona pattern, act as a prompt critic, perform and give the output that I provide you a grade in terms of how well it matches the expectations of the prompt designer. I am going to give you examples of grading prompts. And so we could have gone and done something like that. I did a relatively simple prompt, but we could do a much more sophisticated prompt using some other patterns. Again, it's going to generate an explanation, and then at the end of it, it should generate a grade for us as well. And so it'll then go through and give us an 8 out of 10. So you notice we got 8 out of 10 one time, we changed the prompt slightly, we got 9 out of 10. Either way, it looks like that's a pretty good output based on our grading criteria and what we want. And so we can use this sort of tool in our toolbox. When we need to evaluate a prompt and the output of a prompt, we don't have to always fall back to having humans look at it. One thing we can do is we can fall back to having the large language model itself evaluate the output. And then we can build different types of automation around that, or we can use that as a trigger to escalate to a human. Now, of course, if we have a lot of really good examples of grading, that helps us a lot. But we don't have to have a ton. If you see in my example, I had just 3 examples of grading the output, and it did a good job of figuring out what I wanted.